here we are at the last lesson for this unit, dilations and symmetry. So you guys have probably heard the word symmetry before. I'm sure you have. You've talked about that in other classes. You may have heard dilation as well, which we're going to talk about actually second. So even though I put dilations and symmetry, that'll be the second thing we're talking about. If you have the notes packet though, you're going to see all of these terms at the top. We're going to focus on just the first two to start with, and then we'll come back to the definitions for dilation. So a line of symmetry, if you do not have your packet, you're going to want to write this down, copy all this stuff down if you don't got your packet. A line of symmetry is any line over which a figure can be folded onto itself, perfectly overlapping. So if I fold a piece of paper, for example, if I got this piece of paper here, and I fold it like this, we would not call this line that I folded it on a line of symmetry, because it's not perfect overlap, right? This piece is sticking out over here, this piece is sticking out over here. This would not be a line of symmetry because it doesn't fold perfectly in half, right? But if I fold it, let's see, this way, I kind of got to experiment a little bit. Hamburger style. Hey, look, this is perfectly overlapping onto itself. We would call this, where I folded it, a line of symmetry. So looking at this example here, it's actually what we have. A rectangle is basically a piece of paper. So we want to find where it folds onto itself. So here would be a line of symmetry. And then we also have long ways. You guys know that because that's hot dog style and that's hamburger style, right? Taco or burrito, whatever you guys call it. So that shape has two lines of symmetry. Now, if you try a line of symmetry, say for example, you're looking at this picture and you're like, is this a line of symmetry? Here's what you can do to test. If I come perpendicularly down to my line of symmetry and then perpendicularly away, I need to fall on a point of my shape. So for example here, coming down perpendicularly means at a right angle. So this point, if I kind of come down to this line, yeah, that's perpendicular, right? That's a right angle. And then I kind of estimate the same distance away. Well, if I folded my rectangle over this line, this point would end up folding all the way down here. And that's not a line of symmetry. It has to fall exactly back on the shape. Just like, again, this line of symmetry, this point would fall exactly back on the shape. So that is a line of symmetry. The diagonals are not. Now we also have something probably new to you, which is called rotational symmetry. This is the number of degrees between 0 and 360 that a figure can rotate about itself and appear not to have moved at all. So for example, when I have, again, a piece of paper here, we're going to look at some examples here. It looks like this to start with. Ignore the fact that we've got this thing off to the side. We've got these holes. Imagine this was just a blank piece of white paper, like printer paper, because I don't have any right now. If I rotate it this way, well, that's not rotational symmetry because, again, going from here to here, it doesn't look like where it started. But looking at it here, for example, let's actually look at it on the page. Here, if I rotate it this way, it doesn't look like itself. But if I rotate it once more, hey, that looks exactly like where it started. If I start here and I rotate it, it looks like the exact same shape. This is what we call rotational symmetry. So I was able to rotate this. This is actually a 180-degree rotation. We're going to talk about that later, though. Versus over here, if I start to rotate this, well, right there, it doesn't look like it's the same, doesn't look like it's the same. Hey, it's back to itself. That was a 90-degree rotation. I can turn it again. That's another 90-degree rotation, and it looks like it was to start with. Once more, there's another rotation and another one, and it looks exactly the same as it started with the same orientation. It appears to not have moved at all. So we're going to look at that and talk about how we find what those degrees of rotation are. Now this is actually right here. Oh, whoops. Well, whatever, doesn't matter. You need to add this to your notes wherever you have space if you're in the packet, because you don't have this in your notes. So for rotational symmetry, we can figure out the degrees of rotational symmetry by dividing 360 degrees by the number of lines of symmetry. So we're going to come back to that. We're first going to practice finding lines of symmetry, and then we'll talk about the rotational symmetry. So once more, add that to your notes. That's not in the packet if you have it. Okay, so for this first example, we really did already do this one, determining the lines of symmetry, but again, we'll show it here. With a rectangle, again, I need to be able to fold over this line. So we know we can fold directly down the center, and here's how we know it's a line of symmetry. If I come up to this line and go away, my U should fold over onto R. That's good. The L would fold over onto E. That makes it a line of symmetry. We know we also have the long way as well, because if I were to fold over that line, R would fold down onto E, and U would fold down onto L. That's good. This shape then has two lines of symmetry. So anytime you're trying to test a line of symmetry, ask yourself, if I folded over this line, would my points fall back onto each other? I need R to be able to fall onto a point. Otherwise, it's not a line of symmetry. Let's go ahead and try this next one. So I want you to try this on your own. Think for a second. And again, you have to think, if I were to fold over this line, would my points fall back on each other? It's kind of hard to visualize. Go ahead and try it. Okay, let's see. Now, this is a common one that people think. Say that you thought this was a line of symmetry. Now, I'm going to extend this out here. If I folded this piece of paper in this way, here's what's going to happen. I'm going to fold T up to this line and away. This is where T would fall. That's not on another existing point. So this is not a line of symmetry. If I folded over that point, T would not fall on an existing point. Same thing, A would fall up here. It needs to fall on a labeled point. There is one line of symmetry in this, however. That is a line of symmetry, because if I folded this over this diagonal line, this is the same distance away here. This is the same distance away here. Let me see. Is there any lines of symmetry? Am I wrong? If I fold that over the diagonal. This is stupid. Let me check. Oops. Okay, let's go back. Okay, so after looking at this one, we're going to talk about this. This is kind of what we would call a trick question. This shape does not actually have any lines of symmetry, and let's talk about why. This is a common one to try, but think about folding over that line. If I come up to this line and then fold over it, T is going to end up right there in no man's land. It has to fall exactly on one of the points from the shape. Another common one to try is straight down. Well, already we can see if I try to cut straight down, I'm going to end up with one of these points a little bit closer, and it's only going to fold over to like right here. This one would fold all the way over here. So that's not a line of symmetry either. Same thing, the diagonal also does not work. If you want to try it, cut a piece of paper out. If I fold over this line, what's going to actually happen is E is going to come up here. Again, you have to imagine the points folding over, coming at a right angle. I'm not folding it this direction. You're folding it over at a right angle. That doesn't work. So this actually has no lines of symmetry. That's it. Boom. That is an option. Some shapes you can't fold and they fall back on themselves. It just doesn't work. Okay, we're skipping to example 4. So again, guys, pay attention in your packet. This is example 4. We're skipping example 3 just because I think it's too many examples. So try this one. If I can fold over the line and the points fall exactly onto another point on the opposite side, that's a line of symmetry. Go ahead and give this one a shot. Okay, let's see. This one actually has a line of symmetry down this way. That is a mirror image on both sides. Now, something I should have said is that all of these sides are the same. If that's the case, we can draw a line of symmetry through every single point, starting at A, going to the opposite side. My lines aren't very good. Starting at P, going to the opposite side. So this has 5 lines of symmetry. That is a mirror image on both sides. We can actually have that through every single point. Okay, now we're coming back to the same shape as example 1. We are on example 5 now, so pay attention to what number we're on. We are trying to find the degrees of rotational symmetry. So remember, rotational symmetry, we wrote this down at the beginning, is 360 divided by the number of lines of symmetry. That should make a little bit of sense because you guys should know that 360 degrees is a full turn. Every single shape, if you turn it 360 degrees, yeah, it ends up back where you started. It doesn't matter what the shape is. If I turn this a full turn, yeah, that ends up back where it started. So our answer will never be 360 because everything has 360 degree rotational symmetry. So looking back, our rectangle had 2 lines of symmetry. So all we have to do here, again, we had 2 lines of symmetry, is take 360 and divide it by 2. There once again was 2 lines of symmetry. This is going to tell us how many degrees we can rotate it, and it will end up back on itself. This ends up becoming 360 divided by 2 is 180 degrees. And that should make sense. 180 degrees is a half of a turn, right? Going this way, that's 180 degrees. That's a half turn. It looks exactly like it did when it started. Now, what we're going to see in the next question, or 2 questions from now, is that you want to list all possible degrees of rotation. So what we're going to do is we're going to keep adding the degrees that we find and list out our answers until we reach 360. So 180 is one answer. If I turn my shape another 180 degrees, this ends up being 360. So what this means is 180 degrees is our only degree of rotational symmetry because we don't list 360. Everything has 360 degree rotational symmetry. Doesn't matter. We'll talk, this will make more sense once we look at an example where there are more lines of symmetry. So looking at example 6 now, we found here that there were no lines of symmetry. What do you think this means for rotational symmetry? It doesn't have any. If a shape does not have any lines of symmetry, there is no rotational symmetry either. If I go to rotate the shape, the only way to make it look like it hasn't moved is to make it a full turn. So notice H is kind of in a little bit more than T. If I go to rotate this, yeah, it definitely looks like does not look like how it started. Thought you said it doesn't. HT. Okay, looking at example 6. Now, this is a special case. I did want to look at this one because this is a special case of rotational symmetry. What is this shape called? Do you remember what this shape is called? This is a parallelogram. So basic plain old parallelograms do not have any lines of symmetry. However, there actually is a rotational symmetry here. This is a special case. You might want to add this in your notes. Even though, which we found earlier, there are no lines of symmetry, even though that happens, a parallelogram actually does have one case, parallelogram, of rotational symmetry. If you notice how the H is pulled in a little bit and the T is pulled back, if I flip this over, I'm going to do a half turn. Notice where it lands. This point is pulled in a little bit, this point is out. That does look exactly like where it started. So a parallelogram is a special case. Even though there's no lines of symmetry, it does have 180-degree rotational symmetry. This is a special case that you'll want to write down. Even though it has no lines of symmetry, a parallelogram does have 180 degrees. That one's special, so you want to write that down. Let's try another one that is not so special, that does have lines of symmetry, and so the rule applies. So we found, on example 8, once again, pay attention to what example we are on. We found that we had 5 lines of symmetry, and this is called a pentagon. So what we do is, again, we're going to take 360 and divide by 5. Go ahead and take a moment to do that. I can do it myself. 360 divided by 5. This is 72 degrees. Now, again, here's how we list our answers, though. We're going to keep adding 72 degrees until we get to 360, and then we are not going to list 360 because here's why. If I take my shape here, I'm going to have to rotate the directions, but that's okay. I want to rotate it until a point ends up at the very top again. So here I go. So that, if we notice, P is now at the top. That is a 72-degree rotation. But I can rotate it another 72 degrees and end up back at the same spot again. I can rotate it another 72 degrees and end up back at the same spot with that point at the top. I can rotate it another 72 degrees and end up with this point at the same spot, and then I'm all the way around. So we're going to keep adding 72 degrees to get a list of different degrees that we could rotate it. So I'm going to go 72 plus 72 gives me 144. I'm going to add another 72. Go ahead, I want you to keep going from here. You're going to keep adding 72 and list your answers until you reach 360, and then you're done. Go ahead and give it a shot. Okay, so I can turn it another 72 degrees. 144 plus 72 is 216. I could turn it another 72 degrees. 216 plus 72, that's 288. And I could turn it another 72 degrees. That's 360. Okay, I'm done. Even though 360 is there, these are my answers. We never list 360 because every single shape has 360 degree rotational symmetry. So you want to list all possible degrees. Yes, I could go and take this and go 72. Or I could go straight to 144. That would be 144. 2 72 degree turns. So we want to list all possible answers. And again, we get that by continuing to add the original degrees we found until we reach 360. Okay, we have 2 more examples we're going to get to here, but these are going to go pretty quickly. Now we're talking about dilations. So once more, if you do not have your packet, you're going to want to copy this down. So you guys have probably heard the word dilation before if you've ever gone to the eye doctor. This is where they put the drops in your eyes and your pupil gets bigger, right? They make you wear the funky sunglasses where they just like flip onto your face and they look super dorky because your pupil is so big that it's taking in a lot more light than normal. So when you go outside, the sun is like super bright because your pupil is huge. Your pupil was dilated. The pupil was changed, had the size changed. That's what this is talking about here. A dilation is a transformation that changes the length of each side of the figure by a specified scale factor. And this is what the scale factor is, a multiplier on the coordinates. So this is like saying I am doubling the size of your pupil. The scale factor is 2, right? Or if you're talking about scaling a photo, like if you're on Facebook or something and trying to scale it or for whatever, if I want to scale it by half, that means the scale factor is 1/2. It's what we multiply by to get our new figure. So this is going to cause the object to shrink or to expand. Yeah. Those are both considered dilations, getting smaller or getting bigger. So this works very similarly to the way the translations work. Notice the notation is very similar. Each point is going to have this happen to it. So to start with, we need to know the original points. We are going to perform this dilation by changing each point the way it tells us. So take a moment, go ahead and write down the points for F, T, and I. Yes, even if you have the packet, you need to write down the points in order to get the new ones. Okay, let's check. So F is -4, +6. T is -4, +3. And then I is 0,3. So what we're going to do to each of our points is we are going to apply this. I am going to multiply my x values by 1/2. I'm going to multiply my y values by 1/2 as well. Now, this doesn't always have to be the case, which you're going to see in the next example, but we are doing the same thing to both coordinates. This means 1/2 times your x coordinate. This means 1/2 times your y coordinate. So to get to F prime, and T prime and I prime, we're going to take our x's and our y's and multiply them by 1/2. So let's do the first one. I'm doing 1/2 times -4. Hopefully you can do this in your head, but you got a calculator if not. 1/2 times -4 is -2. 1/2 times 6 is 3. Do it in your calculator if you're not sure. I want you to go ahead and try the next ones as well. You are going to end up with some decimals because we do have some odd numbers, and taking half of an odd number, it's going to happen. So go ahead and try and get the points for T prime and I prime. Take the x, multiply by 1/2, take the y, multiply by 1/2. Okay, let's check. 1/2 times -4, that gives me -2. 1/2 times 3, you guys can write this as a decimal. You can either write 3/2, or you can put this as -2. Do 3 divided by 2 in your calculator, you get 1.5. Either answer is acceptable. We have 1/2 times 0 is 0. We have 1/2 times 3 is once again 3/2 or 1.5. So these are our answers, or this one too. All we do is what it tells us to do. We take our original x, we do what it tells us to do to it. We take our original y, we do what it tells us to do. So we're going to try this last example, example 10. Now notice this one's a bit more complicated. It says 2x plus 1. All we do is we take our original x and plug it into that, get our new answer. Notice that nothing is happening to the y. That means the y does not change. From our old points to our new points, the y stays the same. So start off, once again, with finding your original points. We'll check those first, and then we'll get our new points. Go ahead and find the original points. Okay, so t is 0, 3. Careful, this is 0, 3, not 3, 0. 3, 0 would be right here. This is 0, up 3. I looks like -1, -1. And r is 1, -1. Again, guys, if you cannot get the original points consistently, you will get every single question wrong on this test. You have to be able to get these points consistently. Okay, now I want you guys to go ahead and try and find t prime, I prime, and r prime. Again, I'm going to make this a little bit bigger so I can show it to you when we go over it for a reason. Because I'm going to take my x and plug it in here, spit out my answer. That's going to be my new x. And then my y doesn't change. So my y is actually going to just get copied over. Go ahead and give it a shot. Okay, let's check. So my x here was 0, and I want 2x plus 1. So I have 2, my x is 0, plus 1. My y doesn't change, so my y is still going to be 3. So t prime, you should have gotten 2 times 0 is 0 plus 1 is 1. There's our t prime. So same thing over here. My x is -1, and I want 2 times x plus 1. And I want my y to stay the same. We get -1 for y. So for I prime, we've got 2 times -1 is -2 plus 1. You should have gotten a -1 as well. -1. Yes, we end up at the same spot. That can happen sometimes, right? 2 times -1 is -2. Plus 1 does get us back to where we started. Okay, and for the last one, I want 2x plus 1. Here my x is 1. So 2 times my x plus 1. My y stays the same. So r prime is going to be 2 times 1 is 2, plus 1 is 3, -1, and there's our answer. Boom. Okay, so again, with these questions, all you have to do is what it tells you to do. You just can't get confused. You get the original points, you change them in the way they want you to change them, and then you're done. So I know this was kind of a lot. We're going to do a little bit of a quiz to go back and kind of review these concepts, and then you guys will do the assignment.